In this lesson, you'll learn to graph quadratic inequalities in two variables and solve quadratic inequalities in one variable. How can you find the time a trampolinist spends above a certain height? Trampolining was first featured as an Olympic sport at the 2000 Olympics in Sydney, Australia. Suppose the height, h of t, in feet a trampolinist above the ground during one bounce is modeled by the quadratic function h of t equals negative 16t squared plus 42t plus 3.75. We can solve a quadratic inequality to determine how long this performer is more than a certain distance above the ground. You can graph quadratic inequalities in two variables using the same techniques used to graph linear inequalities in two variables. First, graph the related quadratic equation y equals ax squared plus bx plus c. Decide if the parabola should be solid, because the inequality has an equals, or dashed. It doesn't. For step 2, they say test a point x sub 1, y sub 1 inside the parabola. Check to see if this point is a solution of the inequality. I tend to go on the rule if it's less than, we're going to shade below, greater than, we'll shade above, just like we did for linear inequalities. Step 3, if x sub 1, y sub 1 is a solution, shade the region inside the parabola. If x sub 1, y sub 1 is not a solution, shade the region outside the parabola. Or we could say, if it's greater than, shade above, less than, shade below. It's just as well that we now have calculators with a table feature, because step 1, they don't explain how to graph it, they just say graph the related quadratic equation, y equals x squared minus 3x plus 2. Since the inequality symbol is greater than, the parabola should be dashed. Test a point inside the parabola, such as 1, 2, and sure enough it works. Or, again, as we've noted before, we have a greater than symbol, so we know we're going to shade above or inside the parabola. There's our pretty shaded graphic. But the way I shade it, with a little bit of drawing, if you make a mistake, it's a lot easier to erase. To solve a quadratic inequality in one variable, you can use the graph of the related quadratic function. To solve ax squared plus bx plus c is less than 0, graph y equals ax squared plus bx plus c. Identify the x values for which the graph lies below the x-axis. For less than or equal to, include the x-intercepts in the solution. To solve ax squared plus bx plus c is greater than 0, graph y equals ax squared plus bx plus c. Identify the x values for which the graph lies above the x-axis. For greater than or equal to, include the x-intercepts in the solution. Next, we get to solve by graphing. So again, we could use the table feature to plot points for our parabola, and this time the inequality is greater than. So it's not greater than or equal to, so I just want open circles on the x-axis, and greater than, we're going to go out. So using set builder notation, the set of points that makes this inequality true is x is less than 1, or x is greater than 3. Once again, we're going to graph the related equation. So again, you can be thankful that you have inexpensive calculators that have a table view feature. And grab our points, and this time the inequality is less than or equal to, so they have closed circles on where the graph crosses the x-axis, and they drew a line connecting the dots. Unfortunately, this time it did not intersect to integers, so I'm using quadratic formula to find the exact values of where it crosses. So it crosses at exactly 3 plus or minus square root of 11 divided by negative 2, which gives us an x value between negative 3.16 and negative 0.16, rounding to the nearest hundredth. Fortunately for you, the ones in the assignment are happy integers. I'm going to quickly preview for you some stuff that will come up in courses to come. When we're solving inequalities by graphing, they're going to have us test a value in each region. So one that is smaller than negative 3.16, so they did negative 4, and what do you know, it didn't work. A value between negative 3.16 and 0.16, which we want to work, and it did. Again, if I test a value greater than 0.16, such as 1, it does not work, and we didn't want it to. So that's how you would do a check step for solving by graphing for inequalities. The height of a ball above the ground after it is thrown upwards at 40 feet per second can be modeled by the function h of x equals 40x minus 16x squared, where the height h of x is given in feet and the time x is in seconds. At what time in its flight is the ball within 15 feet of the ground? They're asking when the height will be less than 15 feet. I graphed the related equation in GeoGebra and found the two intersection points at 0.46 and 2.40 rounding to the nearest hundredth. So if we solve this graphically, we'd have a solution between 0.46 and 2.04 seconds. I ran through the last two examples pretty quickly because we're really not going to have much on the problem set for those. Most of our time is going to be spent solving algebraically. And they're going to give us lovely problems such as this, where we can put everything on one side of the inequality and factor. I need factors of -2 to give me a sum of +1, so 2 and 1 will do the trick. +2 and -1 has a product of -2 and a sum of +1. That proposes, again, three interesting regions. X is less than -2, between -2 and +1, and x is greater than 1. So just as with their solve graphically, you could test three values, one in each region. Now this is a less than, so less than we expect our value to be between the two numbers, and 0 worked here. So because the test value of 0 worked, we can conclude that our solution set is x, such that x is a value between -2 and +1. And we'd show that graphically. I would not suggest you writing out this entire table. This is something you do on your calculator, but it's kind of nice to see where the numbers came from. As with linear inequalities, the solution set of quadratic inequality can be all real numbers or the empty set. The solution is all real numbers when all three test points satisfy the inequality. It's the empty set when none of the points satisfy the inequality. They went long on the summary this time. Graph quadratic inequalities in two variables as follows. Graph the related quadratic equation y equals ax squared plus bx plus c. Decide if the parabola should be solid or dashed. Test a point x1, y1 inside the parabola. Check to see if this point is a solution of the inequality. If x1, y1 is a solution, shade the region inside the parabola. If x1, y1 is not a solution, shade the region outside the parabola. To solve a quadratic inequality in one variable, graph the related quadratic function. Identify the x values for which the graph lies below the x-axis. For y is less than or equal to 0, identify the values for which the graph lies above the x-axis. For y is greater than and greater than or equal to.